Okay, so, let's unpack this. Imagine you're embarking on some kind of grand endeavor.
Okay.
Maybe you're a scientist, right? Sending a probe to the moon, carefully picking instruments. They have different payoffs, but strict weight
Right,
limits.
the payload capacity.
Or, maybe it's simpler. You're just packing a backpack for a long hike. Every ounce counts. And different gear gives you different levels of comfort or utility.
Yeah, definitely been there.
You've got this finite capacity, a list of potential things, each with its own weight, its own sort of value to you. And you just can't take everything. The challenge is, well, it's pretty universal, isn't it? How do you choose what to bring to get the absolute most value out of that limited space or weight?
It really is a fundamental optimization challenge, and it
Yeah.
pops up everywhere, like once you start looking for it.
Oh, where else?
Well, think about supply chain logistics or managing a financial portfolio.
Yeah.
Even deciding which features make it into a new piece of software given, limited developer time or budget.
Ah,
Anytime you have limited resources, could be space, time, money, weight, whatever, and a set of options, each with a cost and a benefit, you're basically grappling with some version of this problem.
right. And in the, let's say, structured world of computer science and algorithms, this type of puzzle has a formal name: the knapsack problem.
Exactly.
The knapsack is your container, your limited resource pool. The items are the things you could potentially put in it, each with a cost, like weight and a value. Today, we're diving deep into a specific version. And thankfully for algorithm designers, it's a particularly well-behaved variation,
Uh-huh.
the fractional knapsack problem.
And our guide for this deep dive is a really clear explanation from Hello Algo, specifically their section on this fractional knapsack problem, because it's a solid foundation.
Yeah,
Yeah, it walks us through the problem setup, presents a pretty elegant solution strategy, and crucially explains why that strategy is actually guaranteed to give you the best possible outcome.
perfect. And this deep dive, it's really designed for you, the listener, to cut through any potential jargon and give you a clear and hopefully a lasting understanding of this specific concept. We want this to stick.
Right.
So our mission together is to really get to the heart of the fractional knapsack problem. What exactly defines it? What are its core pieces? And how does its unique characteristic allow for a surprisingly simple yet really powerful solution?
Mm.
We'll explore the clever strategy used to solve it, walk through how it looks in action, understand the sort of mathematical certainty behind why it works every single time for this specific problem. And there's even a cool way to visualize it that makes it incredibly intuitive.
Yeah, it's all about building a robust mental model. So you don't just understand the steps of the solution, but the underlying reasons, and how it fits into the broader world of optimization problems.
Okay, let's start by formally defining it then, based on our source. What's the basic setup we're dealing with?
Okay, so the problem starts with having a collection of, let's say, n items.
Right, and I.
And each item, let's call it item, it has two main properties. First, a weight. The source might write it as WGTI1 using that kind of one-based indexing you sometimes see.
Although often in code, it's zero-based. Like,
Exactly. And second, it has a value, maybe value 1. So item 1 has weight WGTI0, and item 2 has weight WGT1, and so on, up to item n.
got it. Weights and values for each of the n items.
And then you have the knapsack itself. It has a maximum total weight capacity. Let's just call it cap.
Okay, so we've got a list of things, each with a size and a worth, and a container that can only hold so much total size. Pretty straightforward so far. What's the ultimate goal?
Your objective, as the source puts it, is to choose which items, or parts of items, to put into your knapsack.
Parts of items. Okay, hold that thought.
Right. The constraint is that the total weight of everything you put in cannot exceed the knapsack's capacity.
Makes sense. Don't overfill the bag.
And under that weight constraint, your goal is to maximize the total value of everything you've packed inside.
Okay, maximize value, stay under the weight limit. Now, this sounds a lot like the general knapsack problem we mentioned, but you highlighted parts of items, and there's that crucial word in the title, fractional. This is where things get really interesting, isn't it?
Absolutely. That one word, fractional, is the defining feature. It makes this problem solvable in a fundamentally different and actually much simpler way than its close cousin, the 0-1 knapsack problem.
Remind us about the 0-1 version again.
In the 0-1 version, it's strictly all or nothing for each item. You either take the whole item, that's the 1, or you leave the whole item behind, that's the 0.
Right, you can't take half a laptop or, I don't know, a quarter of a priceless vase.
Exactly. You can't saw things in half. But in the fractional knapsack problem,
Here.
here the source explicitly says you can select a part of the item with its value calculated based on the proportion of the weight chosen. This is the absolute key.
So we can slice things up.
It means we can slice, measure out, and take a percentage of any item. Think of a sack of gold dust. You can take just a few grams. Or if you have a barrel of oil, you can take just 1 liter. You're not forced to take the whole barrel or nothing.
And this ability to take fractions, that must make calculating the value added much more straightforward, right? If I decide to take only a portion of items, say I take a weight of it, how does that contribute to my total value?
Well, because you can take any fraction, the value you get is directly proportional to the weight you take. It's linear. And this is where the source introduces the absolutely central concept for solving this problem, the value per unit weight.
Value per unit weight, like dollars per pound or points per kilogram?
Exactly. It's a simple ratio. The item's total value divided by its total weight. So VALI1 divided by WGI1. Think of it as the item's inherent efficiency, or its value density.
Or it's bang for your buck in terms of how much weight it takes up.
Precisely. That's a great way to put it. So if an item weighs, say, 10 pounds and is worth $100,
Then its value per unit weight is $100 divided by 10 pounds, which is $10 per pound.
perfect. And if you decide to take a weight of that item, maybe just 3 pounds, the value you add to your knapsack is simply that weight multiplied by its value per unit weight.
So 3 pounds times $10 per pound, which is $30.
Exactly. 7 times value 1, WGTI 1. This linear relationship where value scales directly with the weight you take is precisely what the fractional nature enables. The source illustrates this point really well. I think it's figure 15-4.
And the source also mentions, the conceptual similarity to the 0-1 knapsack problem. Both deal with items, capacity, maximizing value.
Right, the setup looks similar.
But that single difference, being able to take fractions, like we keep saying, it just completely changes the game.
It simplifies the problem enormously. It makes the optimal solution much, much more accessible compared to the 0-1 version, which usually needs more complex machinery like dynamic programming.
Yeah, I remember that being more involved. So even though the problem structure might look similar on the surface you're considering item and the remaining capacity, the fractional choice just makes the solution approach totally different.
Which leads us directly to the elegant strategy for solving this. Because we can take any fraction of any item, we avoid those complex interdependencies and tricky discrete choices that make the 0-1 problem harder. This allows for a surprisingly intuitive approach.
Okay, and this is where the idea of a greedy algorithm comes in, right?
Yeah.
That's the core strategy the source presents. Can you quickly explain what a greedy approach means in the algorithm world?
Sure, a greedy algorithm is basically one that makes the locally optimal choice at each step. It does what looks best right now.
Without worrying too much about the future.
Exactly. It takes the biggest bite, the shiniest object, the seemingly best option at that moment, hoping that this series of best right now choices will ultimately lead to the best overall solution. It's like always taking the biggest slice of pizza, assuming that'll mean you eat the most pizza in total.
And for the fractional knapsack problem, this greedy intuition actually works perfectly. It leads to the global optimum.
It pays off spectacularly, yes.
Yeah.
The core insight, the real linchpin of the solution, is what you touched on earlier. Maximizing the total value is achieved by maximizing the value per unit weight.
Ah, back to the bang for your buck.
Precisely. If you have limited space, limited weight capacity, the absolute best way to fill that space to get the most value is to prioritize the items that give you the most value for each unit of weight they occupy.
Okay.
You want to fill your knapsack with the densest sources of value first.
It feels incredibly logical when you put it that way. If I have room for just 1 more pound, and item A gives me $10 of value for that pound, well, item B only gives me $5.
You would be crazy not to use that pound of capacity on item A, right?
Absolutely.
So that simple, powerful intuition forms the basis of the greedy strategy.
Yeah.
The source outlines it step by step, I think, in figure 15-5. Step 1 is all about setting your priorities.
Okay, what's step 1?
Sort the items. But
Yeah.
critically, what do you sort them by?
Let me guess. Value per unit weight.
You got it. Sort them based on their value per unit weight, arranging them from the highest ratio, the most value per pound, or per kilo, down to the lowest.
So calculate that value for every single item, and then just create a ranked list. Champions of value density at the top.
Exactly. That sorted list is your roadmap. It tells you the order in which you should even consider packing items. Step 2 is the iterative selection process.
Iterative selection, meaning you go through the list?
Yeah, you go through this sorted list one by one, starting with the absolute best one, the one with the highest value per unit weight. In each round, you greedily consider the item that's currently at the top of your priority list among those you haven't fully packed yet.
Okay, I've got my list sorted by efficiency. I look at the very first item, the most efficient one. Now, what's the decision I make? What do I do?
That brings us to step 3, which is where you actually interact with the knapsack's remaining capacity, cap. You look at the current item and you look at how much space you still have left. And there are really only two possibilities here.
Okay, what are they?
Possibility 1, the current item's full weight fits within the remaining capacity.
So item.weight remaining capacity.
Exactly. If item.weight cap, then this item is super efficient and it's small enough to sit completely. You should absolutely take the entire thing. There's no better use for that amount of weight capacity right now.
So grab the whole item. What happens then?
You add the item's full value to your running total, and you decrease the knapsack's remaining capacity by the item's full weight. Then you move on to consider the next item in your sorted list.
Okay, that's case 1. It fits, take it all, update totals, move on. What's possibility 2?
Possibility 2, the current item's full weight does not fit.
So item.weight remaining capacity.
Right. Item.weight cap. You can't take the whole thing, and this is crucial for the fractional problem. You don't just skip it. This item is still the most value-dense option available to you right now. So you want to cram as much of it as you possibly can into the space you have left.
Ah, so you take just a part of it.
Exactly. You take exactly enough of the item's weight to fill the knapsack's remaining capacity to the brim.
Right, okay. So if I have, say, 7 pounds of space left, and the item I'm looking at weighs 15 pounds, but it's the most efficient one left, I take exactly 7 pounds of that item.
Precisely. You take those 7 pounds, and the value you get from that fractional amount is, just like we discussed, its weight, the 7 pounds you took, multiplied by its value per unit weight.
Okay, calculate the value of that fraction.
You add that calculated fractional value to your total accumulated value.
Yeah.
And critically, once you've taken exactly enough weight to fill the remaining capacity, what happens to the knapsack?
It's full. Capacity is 0.
Exactly. The knapsack is now full. Its remaining capacity is 0.
And does that mean you stop? Is that the end of the process?
That's it. That's the stopping condition. You continue this process, consider items in sorted order, take the whole thing if it fits, take a fraction if it doesn't fit, but fills the rest until the knapsack's capacity is completely filled.
Right.
This happens either when you take a full item that perfectly uses up the last bit of capacity, or maybe more commonly, when you take that fraction of an item that fills it right to the top.
And at that point, you can't add anything else.
Nope, no more room. And the claim is you have achieved the maximum possible value.
Wow, okay. That step-by-step process, it really does make a lot of sense. Prioritize the most efficient things, take whole ones until you can't fit the next whole one, then just shave off a slice of that last best item to use up the very last bit of space. It feels satisfyingly simple.
It is. And the source goes on to show how you might actually structure this algorithm if you were coding it up. It's helpful to think about the data structure first, instead of juggling separate lists for weights and values.
You'd probably group them together, right? Like using a simple structure or maybe a class called item or something that holds both the weight and the value for each item.
Exactly what the source suggests conceptually. You'd have lists of these item objects. Each item object would have properties like, say, item.weight and item.value. This structure just makes life easier, especially when you need to sort them based on their combined properties.
Right. You want to keep the weight and value paired together. And that sorting step is crucial, you said. How does that work with these item objects?
You sort the whole list of item objects, but the key for sorting is their value to weight ratio, their value per unit weight.
So for each item object, you'd calculate item.value, item.weight.
Correct. And the sorting algorithm uses that ratio as the key. It needs to arrange the item objects from the highest ratio down to the lowest, so in descending order.
Okay, items are sorted by efficiency. Now, Edie, that greedy loop you described earlier, how does the source's conceptual implementation lay that logic out?
Okay, so you start with a variable, maybe call it total value, and you initialize it to 0. This is going to keep track of the total value you've packed.
Got it. Accumulator for value.
And you also need to keep track of the remaining capacity in your knapsack. Let's call it remaining capacity, and it starts off equal to the full cap.
Makes sense. Start with 0 value and full capacity.
Yeah.
And then you iterate through the items in that sorted list you just made.
Exactly. You loop through each item in the list, starting from the most efficient one and going downwards. Inside the loop, the really critical check is the current item's weight less than or equal to the remaining capacity in the knapsack?
So if item.weight, remaining capacity, that's the check.
That's the main condition. Now, two cases branch from here.
Okay.
Case one, the item fits fully. The condition if item.weight equals remaining capacity is true.
Take the whole thing.
Right. You take the whole item, so you add its full item.value to your total value, and you subtract its full item.weight from the remaining capacity. You successfully packed a whole, highly efficient item, used up some space, and now you continue the loop to consider the next item in your sorted list.
Okay, straightforward. What's case two?
Case two, the item doesn't fit fully. The condition if item.weight equals remaining capacity is false, which means item.weight is actually greater than remaining capacity.
So you can only take a fraction.
Exactly. The size of the fraction you can take is limited by whatever remaining capacity is left. So you need to calculate the value of just that fraction. How do you do that?
It was the weight we took times the value per unit weight.
Perfect. The weight you take is exactly remaining capacity. And the value per unit weight is item.value, item.weight. So the value you add is
item.value, item.weight, remaining capacity.
you add that fractional value to your total value. Now think about what just happened. You took exactly enough weight to fill the knapsack.
So remaining capacity is now 0.
Right. The knapsack is full. There's no more space left. And the source's logic correctly shows that after you add this fractional value, you should stop. You break out of the loop.
Okay.
Because the problem is solved. The knapsack is full. You can't possibly add any more items or value. You've squeezed the maximum possible value into the available capacity according to the greedy strategy.
I see. So the loop keeps taking whole items, updating capacity and value until it hits one item that's too big. It takes just enough of that item to fill the remaining space, adds the corresponding fractional value, and then stops because the capacity is now 0.
Precisely.
Okay, let's try a quick conceptual example just to make sure this locks in. Suppose my knapsack capacity cap is 50 pounds.
Okay, 50 pounds.
And I have 3 items, let's say.
Weighs 10 pounds, value $60.
Weighs 20 pounds, value $100.
There's 30 pounds, value $120.
Great example. Let's follow the steps. First, we need that crucial metric, value per unit weight for each item.
Okay. Item A is 10 pounds. That's $6 per pound.
Good.
Item B is $100 per pound. That's $5 per pound.
Right.
Item C is 30 pounds. That's $4 per pound.
Excellent. Step 2. Sort them by this value per unit weight highest first.
Okay, A is 6 pounds, B is 5 pounds, C is 4 pounds. So the sorted order is A, then B, then C.
Perfect. Knapsack capacity starts at 50 pounds. Total value starts at $0. Let's start the loop.
First item is A.
Look at item A. 10 pounds, $60 value, 60 pounds efficiency. Does its weight, 10 pounds, fit in the remaining capacity, 50 pounds?
10 is less than or equal to 50.
Okay, so we take all of item A, add its full value, $60 to the total. Total value is now $60.
Right.
Subtract its full weight, 10 pounds, from the capacity. Remaining capacity is now 50 minus 10, which is 40 pounds.
Okay. Knapsack contains item A. Value is $60. Capacity left is 40 pounds. Next item in the sorted list is B.
Look at item B. 20 pounds, $100 value, 5 pounds efficiency. Does its weight, 20 pounds, fit in the remaining capacity, 40 pounds?
Yes, 20 is less than or equal to 40.
So we take all of item B, add its full value, $100, to the total. Total value is now $60 plus $100, which equals $160.
Okay.
Subtract its full weight, 20 pounds, from the capacity. Remaining capacity is now 40 minus 20, leaving 20 pounds.
All right. Knapsack now has item A and item B. Total value $160. Capacity left is 20 pounds. Next item in the sorted list is C.
Look at item C. 30 pounds, $120 value, 4 pounds efficiency. Does its weight, 30 pounds, fit in the remaining capacity? 20 pounds.
No. 30 is greater than 20. It doesn't fit.
Correct. So we can't take the whole thing. We take a fraction of item C. How much weight of item C can we take?
Exactly the remaining capacity, which is 20 pounds.
Precisely. We take 20 pounds of item C. Now calculate the value we get from this 20-pound fraction. It's the weight taken, 20 pounds, multiplied by item C's unit value, $4.
So 20 times $4, that's $80.
Right. Add this fractional value, $80, to the total value. Total value is now $160 plus $80, which is $240.
Okay, total value is $240.
And what happens to the remaining capacity? We just used up the last 20 pounds.
It's 0. 20 minus 20 is 0. The knapsack is full.
Exactly. And since the knapsack is full, remaining capacity is 0, what do?
You stop. break the loop.
Correct. The process terminates. The maximum total value we could get, according to this greedy strategy, is $240, and that was achieved by taking all of item A, all of item B, and 20/30ths, or 2/3 of item C.
That walkthrough really makes the process incredibly concrete. Seeing the numbers change step by step helps a lot.
Okay, so the algorithm seems straightforward enough. What about the computational resources needed? Like, how much time does it take? How much memory? The source mentioned time and space complexity.
Right, let's think about the cost. There are essentially two main parts to the algorithm we just walked through. First, you have to sort the items. Second, you have to iterate through them in that sorted order.
Sorting and iterating, okay.
For time complexity, the source specifically notes, apart from sorting, in the worst case, the entire list of items needs to be traversed. Hence, the time complexity is ON. Now, that ON refers just to the part after you've already sorted the items that loop where you're picking items and filling the knapsack.
Means you just go through the list once. Pretty much, yeah. You go through the sorted list, maybe not even all the way if the knapsack fills up early. And for each item you consider, you do a constant amount of work. A comparison, maybe some arithmetic, updating a couple of variables. So that traversal part itself is very fast. It's linear with respect to the number of items.
But wait, sorting takes time too, right? You can't just ignore that. And isn't sorting usually slower than just ON?
You're absolutely right. That's the key point. Standard comparison-based sorting algorithms, like merge sort or heap sort, which are efficient and commonly used, typically have a time complexity of where ends the number of items you're sorting.
Okay, for sorting.
And since the greedy selection loop afterwards is faster, the overall time complexity of the entire fractional knapsack algorithm is actually dominated by the sorting step.
So the total time is really...
Yes. The ON from sorting is the bottleneck, which, generally speaking, is considered quite efficient for many problems. It scales pretty well as the number of items grows.
Okay, time complexity overall. What about space complexity? How much memory does this algorithm need?
For space complexity, the source points out the main requirement. You need to store the information about each item.
Like that list of item objects we talked about, holding the weight and value for each.
Exactly. If you're creating a list of n such objects, you naturally need space proportional to n. Some sorting algorithms, like merge sort, might also require some additional auxiliary space, often as well. But usually when discussing the space complexity here, the dominant factor considered is the space needed just to store the input items themselves.
So roughly proportional to the number of items.
Right. The space complexity is generally stated as you need enough memory to hold the representation of your n items.
Okay, so relatively efficient in both time and space. It's good news. But we've relied a lot on intuition here. This greedy idea of picking the best value per pound first feels right, especially with that example. But how do we actually know? How do we move from this seems like the best approach to this is absolutely mathematically guaranteed to give the maximum possible value?
Yes.
Couldn't there be some weird counterintuitive combination, maybe taking less of a super efficient item to make room for slightly less efficient ones that happen to fit together perfectly, and somehow that adds up to more total value?
That is the critical question, isn't it? And it's where we need a formal proof.
Right.
We need to show that the greedy strategy isn't just a good heuristic. It's provably optimal for this specific problem.
Okay.
The source uses a very common and powerful technique for this. Proof by contradiction.
Proof by contradiction. Okay, I remember this from math classes. You assume the opposite of what you want to prove is true, and then you show that this assumption leads to some kind of logical impossibility, a contradiction.
Exactly. That contradiction proves your initial assumption must have been wrong.
So in our case, what are we assuming to be false? What's the opposite we start with?
We want to prove that the greedy strategy, sorting by unit value and taking items greedily in that order, yields the optimal maximum value solution. So for the proof by contradiction, we have to assume the opposite. We assume that the greedy strategy is not optimal.
Okay, assume greedy is wrong. What does that imply?
If the greedy solution isn't the best one, it implies that there must exist some other way to fill the knapsack, some other selection of items and fractions that achieves a higher total value than the greedy approach did. Let's call this hypothetical better solution the optimal solution.
So we're imagining there's this super knapsack packed somehow differently that managed to beat the greedy score.
Exactly. Now let's think about this hypothetical optimal solution. If it's truly different from the greedy solution and it gets a better result, it must have deviated from the greedy strategy somewhere. The most fundamental greedy choice is always prioritizing the item with the absolute highest value per unit weight.
Right.
So let's focus on that. Let item X be the item with the very highest value per unit weight among all available items. If our hypothetical optimal solution is different from the greedy one, maybe it didn't take as much of item X as it could have. Perhaps it took none of X or less of X than the greedy algorithm would have stuffed in before the capacity ran out or it moved to the next item.
Okay, so the optimal solution is somehow less heavy on item, the most efficient item, than the purely greedy one would be.
Right. Now comes the core of the proof, the thought experiment that leads to the contradiction. The source describes this kind of logic. Take the supposed optimal solution in the knapsack. Since it's optimal, we can assume it filled the capacity completely. Otherwise, you could just add more of something and increase the value, contradicting optimality.
Makes sense. An optimal solution wouldn't leave empty space if there are valuable items left.
Now, because this solution wasn't fully greedy with respect to item X, it must contain some amount of another item, let's call it item Y, where item Y has a value per unit weight that is less than the value per unit weight of item X, or perhaps it contains less of item X than the knapsack capacity would allow.
Okay, so there's either some less efficient stuff in there, or there's still room that could have been filled by more of the most efficient stuff.
Let's consider the first case, which is simpler to visualize. Suppose the optimal solution contains some amount of item. Let's perform a swap. Let's remove a tiny amount of item from the knapsack, say 1 unit of weight.
Okay, take out 1 pound of the less efficient item. That frees up 1 pound of capacity.
Exactly. Now, what do we do with that freed up pound of capacity? We use it to add 1 pound of item, the item with the absolute highest value per unit weight.
We're swapping out a pound of something less efficient for a pound of the most efficient item.
Precisely. We swapped equal weights, so the total weight in the knapsack remains exactly the same. It still fits within the capacity cap. But what happened to the total value in the knapsack after this swap?
Well, since item X has a higher value per pound than item Y, replacing a pound away with a pound of must have increased the total value, right?
Absolutely. By definition, since it has the highest unit value, the value gained by adding a pound of X is strictly greater than the value lost by removing a pound of Y. The source confirms this line of reasoning. Since the unit value of item X is the highest, the total value after replacement will definitely be greater than res, where res was the total value of the solution we initially assumed was optimal.
And there it is, the contradiction.
Exactly.
We started by assuming we had an optimal solution with value res. But then, by doing a simple swap, replacing a bit of a less efficient item with an equal bit of the most efficient item, we created a new solution. This new solution fits in the exact same capacity, because we swapped equal weights, but it has a higher total value than res.
Which directly contradicts our starting assumption that res was the maximum possible value, the optimal solution.
So the initial assumption that an optimal solution could exist without fully prioritizing the item with the highest value per unit weight, up to the limit of capacity, must be false.
That's the power of the proof by contradiction here. It forces us to conclude that the optimal solution must include as much as possible of the item with the highest unit value. Then, for the remaining capacity, the same logic applies. You must include as much as possible of the item with the next highest unit value, and so on.
It cascades down the sorted list.
Exactly. As the source generalizes this idea, overall, items with greater unit value are always better choices. The greedy strategy isn't just a good guess or a heuristic in this case. It's the mathematically proven path to the maximum value for the specific constraints of the fractional knapsack problem.
And the key insight the proof gives us is that, for this problem, the ability to take fractions completely smooths things out. There's no hidden benefit to some complex combination. Prioritizing value density is always the best move.
Yes, that fractional nature is what makes the greedy strategy provably optimal here. It eliminates the tricky combinatorial aspects you see in the 0-1 version.
That is incredibly satisfying. It really confirms that the intuitive bang-for-your-buck approach is genuinely the optimal one because you can slice and dice the items.
It is. It's a nice alignment of intuition and mathematical proof.
And the source even offers another way to understand this, right?
Yeah.
A sort of cool visual way, geometric perspective. I think it was figure 15-6.
Yes, this analogy is fantastic for building intuition. Imagine each item isn't just abstract numbers, weight, value, but a physical rectangle.
Okay, a rectangle for each item. What determines its shape?
2 things. The width of the rectangle represents the item's total weight.
Okay, width is weight.
And the height of the rectangle represents.
Well, what do you think?
It's got to be the value per unit weight, that efficiency score.
Exactly. The height is the value density value weight. So think about what different items look like now. A heavy item with low value per pound is a wide, short rectangle.
Right, squat. A light item with a high value per pound is a narrow, tall rectangle.
Skinny and tall. Okay, I can picture these rectangles.
Now think of your knapsack's capacity. Geometrically, this is like having a fixed total width available along the x-axis. You can arrange these item rectangles side by side if their total width cannot exceed.
So the knapsack capacity is my total allowed horizontal space.
Precisely. And what's the goal? Maximize total value. What does total value correspond to in this picture? Remember, area, width, x, height.
Width is weight, height is value weight. So area, weight, value weight, which is just value.
You got it. The area of each rectangle represents the total value of that item. So the problem transforms into how do you pack rectangles or parts of rectangles into a fixed total width such that you maximize the total area of the rectangles you've packed.
Okay, I'm trying to pack rectangles into a box with a fixed width, and I want the biggest possible total area inside.
Exactly. Now, how does our greedy strategy look in this geometric view? What was the first step of the greedy algorithm?
Sort the items by value per unit weight. Highest first.
Right. And what does value per unit weight represent geometrically?
A height.
So sorting by unit value means arranging your collection of rectangles from tallest to shortest.
Okay, line them up. Tallest on the left.
Now, what was the next step? Iterate through them, taking as much as possible. Geometrically, this means you start placing the tallest rectangle into your box at the left edge. Then you place the next tallest one right next to it, and so on. You keep adding the next tallest rectangle side by side.
Filling up the box's width from left to right with the tallest ones first.
Until you get to a rectangle that's too wide to fit entirely in the remaining space within your total width limit.
Right, like in our example with item C.
Exactly. Now, because this is the fractional knapsack, what can you do with that last rectangle that doesn't quite fit?
You can slice it.
Precisely. Geometrically, this means you just take a vertical slice of that last rectangle. You cut off a piece whose width is exactly equal to the remaining space you have left in your box's total width.
And the value I get from that slice is just the area of that partial rectangle, right? Its width, which is the remaining capacity, times its full height, which is the item's unit value.
Exactly correct. This visualization powerfully demonstrates why the greedy strategy is optimal here. By always picking the tallest rectangles first, you are absolutely ensuring that every single unit of width, which represents weight, that you fill in your limited space, contributes the maximum possible amount of height, unit value.
You're maximizing the height contribution for every bit of width you use.
Which directly maximizes the total area, total value you can pack within your knapsack's fixed width capacity. You are quite literally packing the densest value, the tallest rectangles first, until you run out of horizontal space.
That geometric perspective really does lock it in. It stops being just an abstract algorithm and becomes this very intuitive process of, well, prioritizing density to fill a fixed volume or weight limit most effectively. It makes perfect visual sense.
It really highlights how the underlying mathematical structure of the problem, especially that linear value contribution from fractional parts, aligns perfectly with our simple greedy intuition.
Okay, fantastic. So let's just quickly recap the journey we took into the fractional knapsack problem. We started by framing it with those relatable scenarios, limited resources, needing to maximize value, like packing a bag or planning a mission.
Yep. Then we formally defined the problem. You have n items, each with a weight and a value. You have a knapsack with a limited capacity. And the crucial distinguishing feature, you can take fractions of items.
Right, where the value scales linearly with the portion taken. That led us straight to the key concept, value per unit weight or value density.
And that concept was the foundation for the elegant and surprisingly straightforward greedy strategy.
Which was, step 1, calculate value per unit weight for all items. Step 2, sort the items based on this ratio, highest to lowest.
Step 3, iterate through that sorted list. For each item, if the whole thing fits in the remaining capacity, take it all. Update value and capacity.
If the whole thing doesn't fit, take just enough of a fraction of that item to fill the remaining capacity completely. Calculate the fractional value, add it to the total, set capacity to 0, and stop.
Exactly. We walked through how this could look conceptually in code, maybe using an item structure, and that core loop logic checking item.weight equals remaining capacity.
We solidified it with that nice little numerical example with items A, B, and C, arriving at the $240 maximum value.
And we discussed the algorithm's efficiency, noting its overall time complexity, mainly due to the sorting step, and its space complexity for storing the items.
And then, maybe most importantly, for really understanding why it works, we delved into that proof by contradiction.
Right, showing that assuming any non-greedy solution could be optimal leads to a logical impossibility. You can always improve a non-greedy solution by swapping in more of the higher density item.
Which proved definitively that the greedy strategy of prioritizing value per unit weight is guaranteed to yield the maximum possible value for this specific fractional knapsack problem.
And finally, we explored that intuitive geometric analogy. Items as rectangles, width is weight, height is unit value. Knapsack capacity is total width. Greedy means packing the tallest rectangles first.
Which visually confirms that you maximize the total area value within the limited width capacity by prioritizing height, unit value.
Absolutely.
So the core takeaway seems crystal clear. For the fractional knapsack problem, when you can take fractions, the path to maximum value is paved with that simple greedy rule. Prioritize items by their value density, their bang for your buck.
Yep. There's no complex workaround that beats it in this case. It's provably the best method.
And understanding the structure of problems like this one, where greedy algorithms do work perfectly, gives you, the listener, a really powerful tool. It helps you recognize similar optimization opportunities that might pop up in completely different contexts.
It really does. It provides a specific, guaranteed optimal solution for this important problem type.
But our exploration today also leaves us with a really interesting question to ponder, doesn't it? Something for you to maybe chew on. We've seen how beautifully and perfectly this greedy approach solves this specific problem, the fractional knapsack, precisely because you can take fractions. But does a greedy strategy always lead to the optimal solution for all types of knapsack problems?
Like the 0-1 version.
Exactly. What about that 0-1 knapsack problem we mentioned, where you can't take fractions? You have to take the whole item or nothing. Can a simple step-by-step best choice right now strategy still guarantee the best overall result then?
That's a great question.
Or could making the locally optimal choice at some point lead you down a path where you miss the true global optimum because you didn't save space for a different combination of whole items later? Sometimes, maybe the locally best move isn't globally best. That difference between problems where greedy works, like fractional knapsack, and where it might fail,
Yeah.
well, that's a fascinating rabbit hole all its own.
It really highlights the importance of understanding the specific constraints and structure of the problem you're trying to solve. The answer isn't always the same.
Definitely something to think about.